University, where he is also serves as the director of the Texas Tech University Water Resource Center, a university-wide center focused on sustainable water resources problems. He is also an honorary professor of the Faculty of Civil and Environmental Engineering at Jamia Institute of Technology, Ethiopia. He is currently the editor-in-chief of the Journal of American Water Resources Association, a preeminent journal on multidisciplinary water resources research published by Wiley InterScience. Prior to joining Texas Technical University in 2012, Dr. Udamuri was a professor at Texas A&M University, Kings Valley, for 11 years, where he is also headed the National Science Foundation, funded by funded Center for Excellence in Science and Technology, research on environmental sustainability in semi-arid coastal areas. His primary research interests are in the broad area of water resources with an emphasis of developing and applying the mathematical modeling techniques to pressing water resource problems. His current focus is on the use of stochastic risk assessment methods to assess risks to water systems under climate change, and the use of big data and physics inspired machine learning methods for sustainable water resources engineering. He has authored over 85 peer reviewed journal articles and book chapters. He also has authored two textbooks and is in the process of writing another on water resources planning and management. Dr. Udamuri research has conducted research in excess of 18 million and has received funding from a wide range of federal, state, local, and international agencies such as the National Science Foundation, US Department of Agriculture, US Department of Defense, National Oceanic and Atmospheric Administration. In the year 2016, he was an invited panelist to discuss national water policy organized by Office of Science, Technology and Policy of the President Obama's White House. He has made several invited presentations worldwide and recent organized a specialty conference on improving water infrastructure through adaptive resilience. Dr. Venki Udamuri has taught a broad range of courses at both undergraduate and graduate levels in the area of fluid mechanics, engineering hydrology, surface water, groundwater, hydrology, groundwater contamination transport. He leads the systems thinking initiative within the civil engineering department and has developed a new graduate certification curriculum titled Data and Informatics for Civil Engineering. Dr. Otamuri has active collaboration in many parts of the world, including Brazil, China, India, Oman, and Ethiopia. In 2018, he was selected by the Government of India Ministry of Human Resources to present two short courses on groundwater modeling and water resources informatics as part of their global initiative of academic networks, that is GAN network program in the year 2018. So now I am handle the session to Dr. Venki Udamuri, sir.
Thank you. Thank you for that introduction. I hope you all can hear me well.
Yes, sir. Yes, sir.
Yeah, great. So I'm going to go ahead and talk today about groundwater contaminant transport and remediation. I want to thank Dr. Ramarao for the invitation to give this presentation. So I'm very excited to be presenting this. And what I'll do is generally give you a broad overview of how do we do groundwater? What are various things we do when it comes to groundwater contaminant transport modeling as well as remediation. So again, I try to keep it as brief as possible so that we'll have time for questions and answers in the end. So let me start off by talking about what is groundwater. You probably all know what groundwater is. So we have a surface environment, and then down below that surface environment is our subsurface environment. And our subsurface environment can be broadly categorized into two zones or two areas. Okay, the one which is the shallower environment is what we refer to as the vadose zone or the partially saturated zone, because if you go back and look at the phase diagram here, you have air, water, and soil. So there are three phases in this subsurface vadose zone. And down below, there is an area which is demarcated by the water table, and that is the zone of saturation. So you have the pores are fully saturated with water. So again, if you look at your basic phase diagram, there are two phases here, the waters which fill up the pore spaces, and then the solid matrix which holds that, which causes that pore spaces. So if you look at the vadose zone, the water is held in tension because you have two fluids, air and water, competing for that pore space. So they're trying to push each other out. So that's why the water is held under tension. So it's the surface tension that holds that water. And the water is essentially under compression because the pores push that water. As the pores are fully saturated with water, the rock matrix is pushing that water, which causes the flow of groundwater. So when we talk about groundwater, we are only talking about water that's below this water table, or in subsurface environments where the pores are fully saturated with water. So there are many types of groundwater environments. Aquifers are basically units that produce large quantities of water, so that's of interest to us. If we want to develop a water supply project, we typically look for aquifers because there is sufficient amount of water of good quality usually as well as sufficient amount of quantity. But you could have other types of geological formations, namely the aquitards and the aquifluids. Aquitards, as their name comes, essentially the water can move through them, but it moves very slowly. So in terms of water supply, we really don't develop sources in aquitards. But when it comes to contaminant transport, aquitards play a very big role because the contaminants can get trapped in aquitards and sit there for years and years and years, and sometimes centuries, and slowly leach into the underlying aquifers. So when we deal with contaminant transport, aquitards play a very big role as well. Aquifluids, on the other hand, have water, but they don't really transmit water. But again, from a contaminant transport perspective, they're very important because the contaminants can get trapped into aquifluids and then diffuse out very slowly over a very long period of time, causing contamination. So when we talk about water supply projects, typically we're interested in aquifers. When we talk about contaminant transport issues, we look at aquifers, aquitards, and aquifluids. Of course, you also have aquifuges, which are geological formations that are neither porous nor permeable. So we don't pay much attention to aquifuges, but nonetheless, they can be important sometimes in how they affect the movement of water. Aquifers are basically water bodies which are where the pores are fully saturated with water. There are many ways in which we can define these aquifers. One way to define them is to use what is called as the hydraulic definition, which is the unconfined and the confined aquifers. You probably have talked about this in your geotech classes as well. And essentially an unconfined aquifer is characterized by a water table. And this water table, or the surface of that water table, is open to atmospheric pressure. So there is atmosphere pressure acting on this, or roughly atmospheric pressure acting on that water, on the surface of the water table. And of course, the pressure increases as we go down in depth. And a confined aquifer is an aquifer that is confined between two confining layers, usually of very low permeability. Typically, these are rock formations, or these could be clay formations. So they basically confine the water or the aquifer that's in between. And as a result, the water is under pressure because it has an overburden pressure from the top that puts it under a pressure higher than the atmospheric pressure. So typically, if you put a well in the right place in a confined aquifer, you can get what's called as an artesian well, or a well that flows by itself, of course, saving you a lot of energy. But in general, when we put a well in a confined aquifer, the water level rises much above that confined aquifer. And that is what we call an artesian well. So that's because the pressure is released. The pressure here is atmospheric, and the pressure here is some positive pressure. So the water moves from higher pressure to lower pressure till it equilibrates and causes the water in that well to move much higher than where the aquifer actually is. Whereas the water table is what defines the pressure in an unconfined formation. Even though we talk about these confining units, they are strictly not impermeable. For some purposes of analysis, we assume this to be impermeable, but in reality, these confining units typically are aquatards. So if we have a contamination present in that aquatard, then it can slowly leach in and leak into these confined formations, or it can move up into unconfined aquifers and contaminate the aquifers. Another type of aquifer that's very common in bedrock conditions, like in India, are the perched aquifers. These are small sand deposits that are very shallow, and they usually supply water to dug wells or very shallow wells. So these are generally under perched conditions. So there's a clay lens or something that will cause water to store and create an aquifer, a very small aquifer that cannot be exploited for very large water uses, but can be used for smaller demands to meet smaller demands as well. So typically, the shallower the aquifer is, the more susceptible it is to contamination, because contamination usually happens at the surface. We do something in the surface that causes contamination. And so the first aquifer, either the perched aquifer or the unconfined aquifers, are affected. That doesn't mean that the confined aquifers are not affected by contamination. They can also be affected, as I said, if a contaminant gets into this aquatard, it can serve as a very long source of contamination. So let's talk about groundwater a little bit. Groundwater is the most extracted substance in the Earth's crust. Typically, we use about 1,000 kilometer cube per year of water. That's a lot of water. So just to give you some perspective, the city of Guntur is about 60 square miles or 60 square kilometers in area. So if I have a head of about 15 kilometers of water on top of it, that is the amount of water that would be used. Imagine the water on top of this area extending to about 15 kilometers all the way up into the atmosphere, and that would be the amount of water that we use. So we use a lot of water, and India, of course, is the largest user of groundwater. About 25% of the world's groundwater use happens in India. Of course, China and US are the two other larger users of water. And mostly water is used for ag, but increasingly this is being exploited for municipal use. Everybody kind of knew about what happened last year when Chennai ran out of water. So there's scarcity of water, both in terms of the quantity of water, but also in terms of the quality of water. So both these issues are extremely important in a place like India. So what defines groundwater use? So when can we put groundwater to use? Groundwater is a resource, we want to use it. Groundwater use is affected by quantity and quality. So we generally use the word water availability as a catch-all term, like as something that captures both the quantity and quality. So when it comes to quantity, it's largely controlled by hydrogeology. We model groundwater systems using Darcy's law and conservation of mass. Again, you must have studied Darcy's law either in your hydrology or in your geotech classes. And we need aquifer properties like the aquifer transmissivity and storage coefficients. Those are the two basic properties associated with any aquifer, or the hydrogeological characteristics of the aquifer. So transmissivity, briefly, is the ability of the aquifer to transmit water. It is the hydraulic conductivity times the thickness of the aquifer, the thickness of the saturated layer in unconfined formations. Storage coefficients, this defines how much of a hydraulic head drop do we get if we remove a certain amount of water over a unit cross-sectional area. So storage coefficient, water is drained by different mechanisms, depending on whether you're in unconfined aquifer or in a confined aquifer. In unconfined aquifer, water is drained due to gravity. So you use the term specific yield, or what is called as the drainable porosity, or the amount of water that can be removed under the influence of gravity. In confined formations, the water is under pressure, so it's really the compression and expansion of that water that causes the water to move out. So the compression of the aquifer matrix and the compression of the water itself is what causes the water to be expelled out of the system. So we use the word storage coefficient. Storage coefficient is more a catch-all term, a more generic term that says how much of a hydraulic head drop do we see over a cross-sectional area for a given amount of water that we remove. So one of the things to get these information, we do what are called as a pumping test. So we drill wells and then start pumping water. So, and then we see how the water level drops over a period of time. And then we tend to equilibrate it for a while, which is called the pre-pumping period. And then we pump so that the water comes down. And then we stop pumping at a time and see how the water recovers back. Of course, as we pump water, the hydraulic head drops in the aquifer. So locally, the well at this point in time has a lower head compared to the surrounding area. So the water starts to flow towards the well, and that process is called recovery, and it tends to get back to some equilibrium sometime later. So typically we do a drawdown test and a recovery test. One phase where we are pumping and another phase where we are not pumping, and we try to get water. These experiments have become somewhat easier over the years, especially over the last 10 years or so. We have started getting really good pressure transducers or water level loggers that can record water level drops at fairly quick intervals, about a second, or even 10 milliseconds or 15 milliseconds. We can do it very reliably these days. And that has improved our ability to get these properties, the transmissivity and the storage coefficients. And again, I show you some different types of logging devices or pressure transducers that we typically install in a well when we do a pumping test to get these characteristics. So once we get those values, we need some sort of a model to describe our groundwater flow, and that comes from what's called as the governing groundwater flow equation. What this groundwater flow equation essentially does is it takes a small piece of your aquifer, and let's call it the representative elementary volume. So it's got an X direction, a Y direction, and a Z direction, and then it assumes that the water flows in and flows out along all these different directions, and then uses Darcy's law to write the movement of water in and out of that system, and then it integrates that over the domain of interest. So that's how we develop the groundwater flow equation. To solve this equation, we usually will have to solve it numerically. So we grid this cross-sectional area both in horizontal and vertical direction. So you have different layers of geologic formations, and then the cross-sectional area of interest to us. So we may have some areas which are inactive, which we turn off, and then so that we can model these irregular boundaries. And then for each of these cells, we have to give what is the transmissivity, what's the storage coefficient, what are the initial conditions, what happens at these boundaries, like is there pumping, is there recharge from the atmosphere, all these types of values that have to be put in, and then eventually we solve this. One thing that's very unique about groundwater systems and groundwater flow equations is that we are actually writing our equations at a macroscopic scale. So if we look at the scale of this representative elementary volume, that's sometimes a square mile. If I'm doing a very large model, we've done some models where we have modeled aquifers in Texas. We have modeled the Ogallala aquifer, which is the largest aquifer in the US, that actually spreads over 8 different states. It's a very large aquifer system. The representative elementary volume in that case is about 5 miles or 5 square miles or something like that. So fairly large systems. So there are many different types of soils when you get a fairly large chunk of that volume of soil. Like if you take a core that size, you're going to see many different soils of very different grain sizes. So what happens is the hydraulic conductivity or the storage coefficients that we are defining is an average over that entire representative elemental volume. So you all know that we cannot measure the average directly. So if I want to say what is the average score in your class, I have to individually know what the individual scores are to get an average score. Like I can't just go measure the average without measuring the individual concentrate. So what happens is we have to indirectly obtain these values. So that process is called as model calibration. So what we do in model calibration is we measure groundwater levels because they're easy to measure, but we really cannot get the hydraulic conductivities or the storage coefficients because we have to use another model to either get it because it's an average property. So we go back and say, let's match those water levels at the wells where we have and try to estimate what the hydraulic conductivity is, what the storage coefficient is, what some of the other parameters are, sometimes the boundary conditions and fluxes associated with the boundary conditions. So that process where we are running the model backwards to get the inputs rather than supplying inputs and getting an output is called model calibration. And model calibration becomes very important. And it's a very challenging problem in groundwater because there is really no unique mathematical solution when we run the model backwards. So running the model forward where we supply inputs and estimate our hydraulic heads is a lot easier problem to solve than taking the hydraulic heads and trying to back out what the aquifer parameters are, but we have to do that. Otherwise, we really cannot calibrate these models. So over the years, we've had some generic groundwater flow simulators. The USGS Smart Flow is a very popular program. It's an industry standard program. These days, we generally use it instead of writing our own code. But when I started getting into this business in the early 90s, MartFlow was there, but it was just getting started. So a lot of groundwater modeling involved writing code and writing these equations and solving these equations. But these days we have some really good codes to help out with the simulation. So putting these models together is a lot easier now than it was, at least from a numerical standpoint. But it's still challenging in the sense that we have to get data from many different places, and we have to deal with a lot of uncertainty when we say, where does this geologic formation really start and where does it really end? And getting that information from spotty data or from cores or soil bores, and then extrapolating over a very large distance or interpolating over a very large distance adds a lot of uncertainty to it that has to be dealt with as we do this modeling process. But that's the flow part of the groundwater equation. So we are just saying we're not looking at any chemicals or any other constituents in that water. We are simply saying how does the water move? And the output of such a flow model would be pressures at all these locations. And of course, that water moves from a higher head to a lower head. So once I have the heads in all these different locations, calculating the direction of the groundwater flow or the volume of groundwater flow becomes easy. And then we typically use a model like this and say, okay, if I put a pump here, because somebody wants to pump water, what does it do? And we can calculate those types of things very easily. So again, these are the governing flow water equations. They're partial differential equations, second order partial differential equations, and T is the transmissivity, Phi is that hydraulic head, and W is the sourcing term, and then S is your storage coefficient. And as you can see, you have X, Y, Z, and T, which are your four states, which are your spatial and temporal coordinates. So what you get is values in space and time. And this is how this work is done. It all started with this little experiment that Henry Darcy did way back in 1857. Darcy was a French engineer who was tasked with bringing groundwater to the city of Dijon. Those of you know, Dijon is very famous for mustard growth. So there's a lot of mustard that's produced in Dijon. And then, so when Henry Darcy did this experiment, he came out with the Darcy's law, which basically said that the flux of the groundwater is proportional to the head gradient So that K is the coefficient of permeability or the hydraulic conductivity, which depends on the fluid as well as the geologic properties. Then there were some pioneering contributions made by several other researchers, Jacob, Theis, and Tush, who eventually helped us get the model in this form. More recent advancements have been that we have some general purpose calibration routines, particularly PEST, and then the use of GIS for data pre-processing and post-processing. And there is quite a bit of interest in looking at unstructured grids and mesh-free methods to do faster computations or to not be limited by how we discretize this our domain. So those are some of the very recent advancements that have happened in this area. So development of a groundwater flow model is the first step of any groundwater investigation. If you're doing a water supply project, your models are going to be very large. They usually span hundreds of miles, hundreds of kilometers or square kilometers. And when you do a contaminant transport problem, your domain is fairly small, typically few square kilometers at best. So the difference really between the two is the scale, but in terms of how those models are set up for the flow, they're essentially the same. So coming to the contaminant portion of the things, what are groundwater contaminants? Well, groundwater contaminants are physical, chemical, and biological constituents that are present in water in higher than acceptable concentration. So if you take groundwater from a well, it's going to contain a lot of these constituents. Okay? It'll have some dissolved solids in it. It'll have a whole host of chemicals because that water has been in contact with the rock matrix for millions of years in some cases, like tens of thousands of years at the very least. So it has that opportunity to interact with that rock matrix, and there is a whole bunch of geochemical reactions that have taken place and caused contaminants or caused chemicals to dissolve in that water. Groundwater systems, the pH typically is around 6.5 to 8.5 in most parts of the world. So that also means that they are very biologically active zones. So you may have, if you have a shallow aquifer, you'll typically have oxygen. So you will have aerobic bacteria. And if you go into deeper aquifers where there is not enough oxygen, you will end up having anaerobic bacteria that use sulfur, or iron, or some other, even carbon dioxide for breathing, for deriving energy. As we do with oxygen. So as humans, we breathe oxygen, so we are aerobes, but there are anaerobic environments where there is no oxygen and you still see life forms, mostly microbial life forms that are present in the back, that are present as well. So just because those chemicals are present or those microbes are present doesn't necessarily mean that groundwater is contaminated. Groundwater is contaminated when the levels of these chemicals or these biological constituents or even physical constituents like heat. If you go very deep into deep formations, you get geothermal energy, so the water can be very hot, and as a result, you can't use it. So you want to dissipate that heat before the water can be put to any use. A lot of times you may want to exploit that heat to heat up something, sort of like heat up buildings. So people use that to do those types of things as well. But generally speaking, elevated levels have to be reduced before we can use it for our purposes. Groundwater contaminants typically are dissolved in water because the sand acts as a filter. You could have colloidal suspension. Most of the microbes that you get are actually colloidal suspensions. Milk, you know that there is water and colloidal suspensions in milk, but generally speaking, you need to do very high filtration to separate those two. It's almost like they're mixed. There can be liquids other than water. These are called the non-aqueous phase liquids, especially if you have petroleum type contaminants or trichloroethylene. A lot of these organics, which tend to be hydrophobic or repel water or very sparingly soluble in water, they tend to be present as a separate phase or a separate liquid, and that causes some challenges. And there can also be suspended materials. Typically, you don't see this in sand and gravel formations, but you can find suspended materials in hard rock or in karst aquifers. Hard rock aquifers are what's there in most part of South India. These are the deeper bedrock aquifers. where you have conduits or channels through which water moves. Cars, there are some cars near Etipotala in Andhra Pradesh, but these are basically limestone formations. So the water dissolves the limestone and then creates conduits for water flow. So there are karst formations there as well. So when it comes to contaminants, humans do cause contamination of groundwater. So those are called anthropogenic contaminants, largely because of improper waste disposal practices. But there is a lot of geogenic contamination that occurs. Like that's because there are chemicals in the rock that get dissolved in water and make the water unfit. We talk about fluoride problems in Andhra. That's largely a geogenic contaminant. Arsenic and fluoride are two very large geogenic contaminants that we worry quite a bit in India as well as in the U.S. Like we're in Lubbock and in Texas, where I study and teach. That's a big issue for us as well. So we have quite a bit of geogenic contamination, but there's also anthropogenic contamination. Usually, the difference between these two is that the geogenic contamination is spread over a very large area. So we don't actively treat geogenic contamination. What we do is we usually pump the water out and treat the water that we have pumped to reduce that geogenic contamination. So if there is fluoride, we don't, fluoride has the matrix may be that it may extend over hundreds of square miles or like hundreds of square kilometers. So we really cannot actively remediate this geogenic contamination zone. What we do instead is we pump water, and before we supply it to people for municipal water supply, we remove that fluoride or bring it down to certain levels. So that's the strategy that we use. When it comes to anthropogenic contamination, this is usually there is a leaking tank or there is some other source that is much more localized. And then we actively treat that groundwater to remove those trace chemicals and deal with it. So the source is very large. We just pump water and treat it as necessary. If the source is small, we tend to treat the groundwater and get rid of that source as possible. So we can classify the sources in 6 different ways. We have sources that are designed to discharge substances, septic tanks, for example, injection wells. Sometimes we do land application of waste because we use them as manure. The sources used to dispose substances, these are your landfills, these are your impoundments. There are sources where you take substances to transport, like pipelines, tanker trucks. And then there is consequence of other activities. So when you do irrigation for farming, you put fertilizers, you put pesticides. You're not really trying to contaminate your groundwater, but some of that excess can leach off and eventually get into groundwater systems. Sources, there might be a source and you may create a conduit by constructing a well or doing some excavation. So again, you have to get permits when you put wells and do excavations to ensure that you're not contaminating the subsurface accidentally as part of your construction activities. And then there are some naturally occurring sources that get exacerbated by human activity. Things like saltwater intrusion, particularly important in coastal areas, upconing of brackish water. There's quite a bit of brackish water in the deeper formations of the earth. And if you're not careful with pumping, that water will actually upcone and come into the shallower portion. So there is unstable water flow that happens because of density differences, and that phenomenon is called upconing. So human activities, as you can see, play a major role. Even though the sources are natural, a lot of times humans exacerbate those sources. So the issue with groundwater a lot of times is that water is the dominant chemical in groundwater. So if I take a typical groundwater system, the molarity of water is about 55.56 moles per liter. So that dominates. Okay. And as an example, I'll show you benzene. Benzene is something you'll find in petrol. So it's a big component of petrol. It's carcinogenic, it causes cancer. It's one of the few chemicals that have been proved to cause cancer, not just we think it causes cancer, but we know it causes cancer. The solubility is about 1750 milligrams per liter. What does it mean in terms of moles? At solubility, the molarity is only about 0.02. But the drinking water standard for benzene is 5 micrograms per liter. This is milligrams. This is micrograms. So it is about 350,000 times, so 350,000 times less than the solubility. So even very, very small amounts of these chemicals can pose toxicity to humans. And that's what makes groundwater remediation or groundwater transport very challenging, is because we have chemicals at very, very, very low dilutions, especially if I want to bring it to drinking. So if I have it at solubility, it's about 0.02 moles. If I want to bring it at the drinking water standards, it's about 6.4 times 10 to the negative 8 moles. Okay, so it's almost like 0.6 nanomoles. So we are going from like 2 millimoles at solubility to about a nanomole. So that is a huge, several orders of magnitude of cleanup that we have to do to meet our drinking water standards. So that's one of the challenges. And as our analytical chemistry capabilities have become better and better over the years, we are able to detect more chemicals in groundwater. So when we detect more chemicals, naturally there is a concern that what are these chemicals going to do to us when we get exposed to them? Some of the new chemicals that we are looking at are pharmaceutical products, for example. So people take a lot of medication and then it gets flushed down. They pass that through the urine or excretia. Eventually, it gets into the subsurface environment. It can get into the water, and somebody else who doesn't need that chemical might be getting very low doses of it through groundwater ingestion. So what is the risk? Are they getting affected by something that they shouldn't be getting affected? So some chemicals are found at nanogram levels, and they still can be harmful to humans over the long run. So a big challenge when we deal with groundwater contamination is dealing with very, very, very low concentrations, or trying to bring that water or the chemicals in that water to such low concentrations that it's virtually undetectable. So that's what the groundwater quality is about. That's what groundwater regulations are about. Typically, we put what is known as some health effects, or there are some secondary effects. And in some places, we don't strictly enforce it, especially for agricultural water use. But they can also be important because when you consume fruits and vegetables that are grown with contaminated groundwater, some of the contaminants can actually get accumulated in fruits and vegetables and cause indirect pathways. Sometimes we want to clean water, so we put like chlorine and disinfectants, and those disinfectants can actually cause harmful byproducts that can be problematic to us as well. And then there are some contaminants like DDT. DDT has been banned for a very long period of time, but we can still detect that in groundwater systems. PFAS are perfluoroalkyl substances. These are very long chain fluoroalkanes. They are the hot topic now in groundwater. They're ubiquitous. You can find them in many locations. So those are of interest as well. So the groundwater contamination is regulatory. There are regulatory drivers, and what we want to do is, how do we get these regulatory drivers? We get them based on what risks do they pose to humans. Typically, there is a level below which they will not pose risks, and then there is a level above which they'll pose risks. So that threshold is what we want to clean up to, or that's the no action level. So we do what are called as health and ecological risk assessments to identify those threshold concentrations. Again, these tend to be very controversial a lot of times because we can't expose humans intentionally to this chemical. So we expose them to rats or to mice, and then try to scale up to humans. So how good is the metabolism in rats or rice compared to the metabolism of humans? There's a lot of debate that toxicologists get into, or we use epidemiological studies where we observe populations that have been accidentally exposed to a pollutant and see what has happened to them. And again, of course, this is also a very challenging field. But once we have a standard, it goes through a long process, and then they do have a considerable uncertainty associated with them, but we try to regulate to that level. That is the risk assessment part. The exposure assessment part tells us what is the current level of risk, or how much is the exposure. So typically we have a contaminated site, contaminants leach in, creates what's known as a groundwater plume. The plume is basically where the groundwater is contaminated. And if you have a well, we start pumping that water and we start taking that groundwater. So we can ingest that groundwater as drinking water. We can inhale vapors, especially if you're taking showers, very hot water. We can come into dermal contact during bathing. We can also come into some indirect dermal contact by irrigating the soils around it and then getting exposed to that soils, or indirectly through milk, meat, and food exposure pathways. So we might use groundwater to produce meat, food, or milk and get exposed that way. So there are many ways in which groundwater actually affects, and not just in terms of your drinking water, but there are other pathways through which groundwater contamination can happen to humans as well. So the exposure assessment is the first step of what we call the RIFS process, of the remedial investigation of feasibility study process. The goal here is to figure out what are the sources contributing to the pollution, who is being affected. And the first question we ask is, what happens if I leave that source in place? If I were to leave this contaminated soil or this contaminated groundwater in place, what is the impact? What is the risk to humans, and what is the risk to other ecological receptors? And this is where and then what are the economic consequences? What's the loss of revenue? What are the expenditures involved in losing that water or providing alternative source of water? What do we do with that? So those are some of the questions. So we use contaminant fate and transport models. Fate and transport models are a lot more complicated than your groundwater flow models, because the contaminant movement is affected by many processes, not just the flow of groundwater. So advection is the movement of contamination due to movement of groundwater, but you could have molecular diffusion, you could have mixing, which is called hydrodynamic dispersion. You could, for some chemicals, they volatilize, so they actually get into the air phase. So that might be of interest. Sorption is when we have a contaminant in groundwater partitioning into the solid matrix, or the solid matrix contaminant getting into groundwater. That process is sorption. We could have some physical and chemical reactions happening in the subsurface, and biotic reactions, which are biological or microbial reactions that are happening in the subsurface. So we have to calculate the fluxes, or the mass of change of mass per time associated with each of these processes and put together. And we use, again, similar to Darcy's law, we make use of Fick's law, we make use of Darcy's law, to get our advection, diffusion, dispersion parameters. These are what are called transport processes. And then we use fate processes, which are basically chemical kinetic processes. So this is very similar to what people do in chemical engineering when they design reactors. So we use those conditions and then put it all together to form equations like this. This is what's called the groundwater transport equation, or the advection dispersion equation. And then we can solve them either analytically or numerically to calculate the concentrations over time. And so here I show you a simple one-dimensional advection dispersion reaction where there is a source, the groundwater is getting contaminated, and we are tracking that contaminant as it moves through our aquifer system. So as it moves, it is interacting with the rock matrix. So that is where there is mass transfer between rocks and the water. So that's the retardation term. There is dispersion, there is mixing going on because it's taking a tortuous pathway. It is not a straight pipe, it's moving through pores, so it mixes. So that's the dispersion. And of course, there is a gradient that is causing the groundwater to move in some direction. And that is the advection part. And as all these things are happening, there could be reactions taking place as well, both due to microbes and due to natural conditions such as pH changes, rock matrix changes, and so on and so forth. So we capture all of these using these models, specify any initial or background concentrations, and then we say, what does this source look like? Our first step is to say this source exists forever and see what the risk is. And then when we come to remediation, we say, what if we cut down this source by half? What if we remove this? What can we do to do this? But we use a very similar model to figure out what will be the concentrations of this well where humans are getting exposed or some ecological receptor is getting exposed. A lot of times when you go into the 2- and 3-dimensional models, you don't have analytical solutions, so you have to do numerical solutions. And solving that model numerically poses its own challenges because a lot of those parameters are unknown. So we have to estimate them again by doing field studies. and then making some good approximation. So eventually what we do is we delineate what's called as a plume. The plume is the footprint of that contamination based on some the outer limit of that plume is based on some regulatory limit. Of course, the middle of the plume is where most of the contamination is. So we have two things that we want to do. The first thing we want to do is we want to make sure this plume stays where it is. It doesn't move forward. Because if it moves forward, then somebody else is going to get contaminated. So that's one issue. So we have to control this plume. The second thing we want to do is we want to shrink this plume or reduce this plume so that the groundwater here can be used as well. So plume control and then plume mitigation are the two parts that are part of the remediation that we do. We collect a lot of different types of data, and we put like cluster type wells, we put nested wells sometimes. We throw in packers and then sample at different levels. So, and then we delineate from different wells what the plume looks like. And we make use of a lot of geostatistical methods to delineate these plumes as well. So in addition to knowing how to solve differential equations, you should also know how to do GIS, you should know how to do geostatistics. So we use those techniques quite a bit as well to do things. And as I said, the two issues are one, regulate your plume, and then reduce your concentration. So that's what remediation does. That's the two goals of the remediation. How do we do remediation? Well, the traditional method is what's called the pump and treat, where we pump water and treat it outside. So that's our first way of doing it. If we have geogenic contaminants, which span over very large areas, this is the preferred approach. Okay? But what happens is this is a very inefficient process to remove contamination or large-scale contamination. So we have to keep pumping and treating forever to clean up these sites. So if we have an anthropogenic contamination, usually we still do this, but we don't do this as much as we used to do in the past. Now we do more passive methods. One passive method is we actually go and put a reactive medium. So we create a trench and then fill it with reactive medium and then make it a permeable barrier so that the contamination actually comes, gets into this reactive medium, reacts, and then what comes outside of that is clean water or remediated water or cleaned up water. So this is one of the passive remediation technologies. If we don't put, so for this, we have to do some sheet piling, we have to do some geotechnical work to create that trench, make sure it's stable, refill it, and then sometimes those pores may clog. So we may have to go and periodically back flush it or remove it or do other things as well. The other option is if our plume is fairly small, instead of putting a big trench and then putting reactive mediums, we can actually put several wells and then do some passive treatment, put chemicals into the well and treat it in situ. So that's also called the in situ treatment. And of course, the last part is what's called as the monitored natural attenuation, where we just monitor to make sure that our plume is stable, things are going down, but we are not doing any active remediation. If at best we are enhancing the microbes that are there in the subsurface and help them help clean up the remediation. So those are the three types of remediation that we do. If we have very high flows, very high concentrations, we have to do some active treatment. If we have reasonably high flows but high concentrations, sometimes we can do this passive treatment. And then under low flow, low concentration conditions, we end up getting to this monitored natural attenuation, which is usually the last step of our attenuation. So we start with active treatment and tend to go in that direction. But a lot of times we can mix and match as well. We might be doing monitored natural attenuation, but occasionally doing some pump and treat when we want water. So generally, we have to use more than one method. There is no one size fits all. There is no panacea, no silver bullet when it comes to remediation. A lot of it is trial and error because we're dealing with a lot of uncertainties and heterogeneities. So just to give you that was a very broad overview of groundwater contamination, the modeling that we do, and the type of data that we collect, and some of the remediation techniques that we use. It's a very exciting field, especially if you like integrated interdisciplinary research. You have to integrate concepts from geological sciences, geotechnical engineering, water resources, hydrology, chemical engineering. So we use concepts from a broad variety of fields, toxicology, sometimes, to come up with knowing how to clean up. So if you're interested in this field, as students, I strongly recommend you to get some good background in geology, hydrogeology, brush up your chemistry, your freshman chemistry, mathematics, especially partial differential equations, numerical methods, and then have a good understanding of field surveying and field methods and laboratory analysis. So as you can see, we use models, we use field data collection and laboratory analysis in conjunction to solve these problems. One of the things that's happening is the sensors have improved quite a bit, and so that is helping us do a lot of field data automation, which means we are collecting a lot of data, a lot more than what we did historically. So now we are exploring tools like machine learning and artificial intelligence and big data methods to solve these problems, to solve and develop contaminant transport problems, like and solve contaminant transport equations. So, so that's another exciting upcoming field where we are integrating artificial intelligence and machine learning to solve groundwater contamination problems. So, so that's a broad overview of this field. So I'm gonna stop here. Thank you all for your time, and then we'll take any questions. And I think we have a few minutes left for Q&A. So are there any questions at this point? I'm unable to see the chat box, so I'm not sure.
Thank you, sir.
Sure.
Thank you for your valuable information and valuable information sharing to all the participants. Before question and answers, I am sharing the feedback link to all the participants. Please, all of you, give your feedback regarding the webinar lecture. After that, please, all of you, ask your question and answer questions through chat mode only. Sir Udamuri, sir.
Yeah.
Please see your chat box, sir. In
yes,
chat
yes,
box, all the audience are asking questions.
Okay, I have the chat box open, but I don't see any
participants. Just now, I shared the feedback link to all the participants. So
yes,
please, all of you, give your valuable feedback and ask the questions to the today's speaker, Udamuri sir. So please, all the participants, ask your questions.
So Kiran Kumar asked a question about has any non-destructive or geophysical investigations used for determination of contamination of groundwater? That's a really good question. Non-destructive geophysical investigations, we do use some of them, but it tends to be a little bit challenging because a lot of times the contaminated sites, especially if they're in urban area, they are very difficult. You get a lot of interferences with the non-destructive testing methods. So there is a lot of interest in using non-destructive testing methods, but a lot of times their usage becomes limited because of the interferences that you're going to get. The deeper formations tend to do very well with geophysical investigations. But when we deal with shallow subsurface, non-destructive methods are a little bit difficult because of the interferences we're going to get with other structures. and the other things that are going on. So that's the answer. Sir, people are talking about COVID-19 virus traces in water body. Is it investigated in any part of the world? Yes, a lot of people are looking at. One of the things about COVID-19 is that COVID-19 can affect your lungs. We all know that. But it can also affect your intestines. Like, there are sites on your intestines, large intestine, that the virus can actually bind to. So you don't see COVID-19 in urine samples, but you do see them in stool samples. And people are trying to use wastewater. They have not really seen active COVID-19 virus yet, but they have seen filaments of COVID-19 virus because the COVID-19 virus is not as strong as an enteric virus. The enteric viruses are what are in your gut. They pass through your digestive system, so they're very, very robust. So you will see them in wastewater or even in groundwater systems. But COVID, you're seeing trace filaments and things like that. So people are trying to use that to say, is there community transmission and things like that. So that's what people are using. Another question is there any modern techniques available for improving groundwater tables, methods for reducing the groundwater contamination? Again, a very good question. We do a lot of recharge, artificial recharge to improve groundwater tables, but they tend to be difficult because they clog up or they use up land space. So particularly in developed countries in Texas in particular, there is a big push to go towards deep well injections as opposed to creating open pits and then trying to percolate water. So in terms of reducing groundwater contamination, really it's education and people not disposing of waste improperly. That's the biggest challenge. So a combination of education and enforcement is typically what's used to improve water quality, so that we are not disposing our waste chemically. What kind of chemicals to be injected for groundwater treatment would you suggest? That would really depend on the contaminant of interest to us. If you're dealing with organics, which can biodegrade, typically we put in oxygen. If you have a deeper aquifer and we know that there are sulfate reducing bacteria or methane reducing bacteria, we try to put those types of things. So that's and again, if you're dealing with things like in situ treatment of fluoride and arsenic, which is another question. Arsenic is a very interesting compound because arsenic is mobile, both during in a reduced form as well as in the oxidized form, which makes it very, very challenging to treat arsenic in situ. In terms of fluoride and arsenic, typically we want to change the redox condition. So we can do it either using microbes, enhancing the microbes that are there, but abiotic reactions can also take place, but they are very difficult to do over large areas. So the in situ treatment techniques for fluoride and arsenic generally are to change your redox conditions, and that are facilitated by putting organic substances, nutrients, and pH control. Can you please elaborate on the role of artificial intelligence in this field, in the field of remediation? Yes, the field of artificial intelligence, so we use neural network type models to develop predictive models to forecast what the concentrations are going to be at different wells. We're using artificial intelligence techniques to do better mapping of our plumes from scarce data sets. We are using fuzzy logic, for example, which is a way to capture decision maker preferences, because when it comes to cleanup of sites, somebody will say, I want to bring it down to drinking water level. Somebody will say, well, we don't need to do it to that level. We can use it for some other purpose. So there could be conflicts among decision makers. So fuzzy logic gives us a way to capture that. There are tree-based models that we have developed, regression trees, random forest type models. The tree-based models are very easy to explain to people because you get a tree and you say, well, this affects this, and also to mine data and get cause and effect relationships that can be used to guide our field sampling, field sampling methods. In addition, we are using cloud quite a bit to collect data remotely. So cloud services where data goes into a cloud and then we can pull it out and put it into our models. So, so that's another area where you're seeing a lot of AI being used. You're using edge computing, which is doing some calculation at the sensor level itself. Can we use groundwater contamination with help of satellite imagery? Not as easy as finding surface water contamination because this is deep, and we don't have satellites that can capture what is happening at that subsurface depth. But satellite imagery sometimes can give us a good idea of the sources of contamination. So, you know, what's happening on the surface can eventually tell what's the likely source. So we do use satellite imagery, but not directly to look at contamination, but indirectly. Sir, is there contamination due to aquaculture? Yes, aquaculture actually, so when you grow shrimp or when you go fish, there is a lot of fecal matter that comes out. The fish are fed with proteins, the food products. So there is a lot of BOD, COD type, and then the nitrogen-based contamination that's associated with aquaculture. A lot of places it's not regulated. Texas is one of those places where it's used. Then the Ashish is asking, thank you, sir, for your lecture. Is it possible to use ancient techniques such as Persian squanats to bring water from distant sources to the contaminated areas? Yes, we do bring water from different sources. The qanats or the flood systems work very well in certain types of formations. We can't really do that in sand and gravel aquifers, but if we have deep bedrock aquifers, we can move water. But again, that's possible. It's used. It's a question of economics. Doing something like that in today's day costs a lot of money, and that would be difficult. Could you please brief about the impact of mining on groundwater in terms of quantity and quality? Mining usually creates, acid mine drainage or other types of metals, heavy metals. So when they get into the contaminated, and when they get into groundwater, redox drives a lot of those reactions. So they change the redox to the groundwater, which can change the microbes, which in turn can affect your water quality. So, and in terms of groundwater use quite a bit, especially if you do open cast mines and other things. People use groundwater as a supplemental source or as a single source. So, so the water quality use goes up as well because of that. So, so mining does affect groundwater both in terms of quantity and quality. So really good questions. You have any more?
Any questions? Please ask the today's speakers. No questions?
All right. So, well, there are no other questions. Thank you all again for coming to this talk. It was useful and informative.
Thank you, sir.
Yeah.
Thank you for sharing the valuable information and clarifying the doubts regarding the webinar to all the participants. No questions. Now I am closing the session.
Okay.
Okay. Thank you, sir. Udamari, sir.
All right. Thank you so much.
Thank you, sir.
Okay. Bye-bye.
Oh, now I am ending the session.